Alright, so you can see that once we rerun this, you realize that we are getting different values for the mu and the sigma, right? So I want to use some Monte Carlo simulation to see on average how will the estimate convert. Will it convert to this? Because by the central limit theorem, if you pick any sample from a distribution that is not normally distributed, right, with a finite mean variance, as the sample size increases, we know that on average the shape of the distribution will approach a normal distribution. The shape of the distribution for the mu will be equal to the population parameter, and sigma will be equal to population standard deviation divided by n, right? So let's use Monte Carlo simulation to check if really on average this estimate will convert to the true population values or parameters. Alright, so Monte Carlo simulation for drifts and volatility. So basically I have to create a function, right? So I'm gonna say pseudocode for simulation, or let's say pseudocode for simulating GBM parameters. Alright, so I'm gonna name this function gbm.sim.estimate. Alright, I'm gonna call this function. In this function, I'll need the number of times I'm going to repeat the experiment. So nsim, that's the number of replications or simulations. Also n, that's the number of returns to the sample. I'll need mu, that's the drift parameter. Sigma, that's the volatility parameter, and also x0, that's the initial stock value, right? Once I have this, I can first of all set a condition or create a container for the drift and volatility coefficient. So I'm gonna say estimate vals. So I'm gonna use the matrix NA, number of rows should be, so this basically saying missing observations or missing values. Number of rows should be equal to the number of times I'm going to repeat the experiment. Then the number of columns should be equal to 2, right? 1 column for the drift and 1 column for volatility coefficients. Alright, so this is basically set our matrix container for drift and volatility coefficient. So from here you can set the looping, looping. I'm going to use the for loop. So for index I in 1 to the number of times I'm going to repeat experiment, I need the returns R, right? So returns So the returns can be defined. I'm going to use the function that I've already created, this function, GBM function, right? This. So that's going to give us the returns or the stock values. So gbm.f, and in this I need n, I need mu, I need sigma, and I also need x0. So once we have this, we are good to go. We can now store in this, in the container that you have created, right? So we can store in the container for each simulation. For each simulation, I want to store in the first column the drift coefficient, so drift.f r. Then we also want to store in the second second column for each simulation. We want to store the volatility coefficient, so let's say store the drift coefficient for each run or simulation. Let me copy this. Then let's just store the volatility coefficient for each run. Right, once we have this, I can put this in a data frame. Right, so df as dot data frame. So I want to put this matrix in a data frame so that it actually looks like a data set. So data frame. Right, so once we have this, we can then look at maybe I can define the name for the data frame. So I'm going to say column names of df. Right, so I want to say the first column I want to name it mu, and the second column should be sigma. Right, then df, so display results. So this is basically going to show the drift coefficient and also the volatility coefficient. So let's quickly run this. Alright, so I'm gonna name this returns, right, or simulated returns. So I'm gonna call the function GBM dot simulation. Right, so Monte Carlo Simulation, and I need to set the parameters. The number of times I'm going to do the simulation should be 1000. Maybe we need 500 stock values. Mu should be equal to 0.05. Sigma should be equal to 0.15. X naught should be equal to 10 as usual. So let's run this. Alright, so once we have this, we can check how this behaves. Let's use head to get the first 6 observations. So let's run this. So here we go. So we can see that for the first run, we can see that it's getting closer to the parameter 0.05 for the mu. For the sigma, it's almost close to 0.15. So for each one, it changes, but we know that by the central limit theorem, as the sample size increases, right, on average this should be equal to, or approximately equal to, the parameter, and this on average should be equal to the parameter. So how do we check that? We can use the apply function to check that. So apply, we need the simulated returns, then margin should be 2 because we want to deal with columns, right? So, and we want to look at the mean on average. So let's run this. Run. So we see that on average is equal to, or approximately equal to, the parameter for the mu, for all the mu's. For the drift coefficient is approximately equal. The same applies to the sigma, and you can actually look at it with a histogram plot. So hist, maybe for the first, we want to check for the drift coefficient. How does it converge? So let's say same. Right, the first column is for the drift. So let's say n class should we go to, let's say 30. Then I can give a color to this to be, let's say blue. Right, let me say main should we go to sampling distribution for drift coefficient. Right, so I think we are good to go. So let's run this. Alright, so we see that on average, per the central limit theorem, right, as the sample size increases, on average the shape of the distribution for this drift coefficient will be approximately normally distributed, and we can see that the mean is actually close to the population parameter. The same applies to the sigma on average, so you can check for sigma. Right, so this is basically how to run a Monte Carlo simulation for the GBM parameters. Please, if you found value in this video, don't forget to subscribe if you haven't, and also turn on the notification to get more updates. Thank you for watching.